Welcome friends to a new session on mathematical modeling. Continuous population models for single species. The increasing study of realistic and practically useful mathematical models in population biology, whether we are dealing with a human population with or without its age distribution, population of an endangered species, bacterial or viral growth and so on, is a reflection of their use in helping to understand the dynamic processes involved and in making practical predictions. The study of a population change has a very long history. In 13th century, an exercise in an arithmetic book written by Leonardo of Pisa involved building a mathematical model for a growing rabbit population. Ecology, basically the study of the interrelationship between species and their environment in such areas as predator-prey and competition interactions, renewable resource management, evolution of pesticide-resistant strains, ecological and genetically engineered control of pests, multi-species societies, plant herbivore systems and so on is now an enormous field. Continuous growth models. Single species models are of relevance to laboratory studies in particular, but in the real world can reflect a telescoping of effects which influence the population dynamics. Let n of t be the population of the species at time t, then the rate of change dn by dt is equal to births minus deaths plus migration is a conservation equation for the population. The form of the various terms on the right hand side of this equation 1 necessitates modeling the situation with which we are concerned. The simplest model has no migration and the birth and death terms are proportional to n, that is linear. Therefore, dn by dt is equal to bn minus dn, where b and d are positive constants and the initial population n of 0 is equal to n naught. Thus, if b is greater than d, the population grows exponentially, while if b is less than d, it dies out. This approach, due to Malthus in 1798, is fairly unrealistic. In the long run, of course, there must be some adjustment to such exponential growth. Verhulst in 1838 and 1845 proposed that a self-limiting process should operate when a population becomes too large. He suggested dn by dt is equal to Rn into 1 minus n by k, where R and k are positive constants. This is called logistic growth in a population. In this model, the per capita birth rate is R into 1 minus n by k, that is, it is dependent on n. The constant k is the carrying capacity of the environment, which is usually determined by the available sustaining resources. There are two steady states or equilibrium states for equation 3, namely n equal to 0 and n equal to k, that is where dn by dt is equal to 0. N equal to 0 is an unstable equilibrium state, whereas n equal to k is stable. An alternative way to see this is via linearization around the steady state. The carrying capacity k determines the size of the stable steady state population, while R is the measure of the rate at which it is reached, that is, it is a measure of the dynamics. We could incorporate it in the time by a transformation from t to RT. Thus, 1 by R is a representative time scale of the response of the model to any change in the population. If n of 0 is equal to n naught, the solution of equation 3 is n of t is equal to n naught k e raised to RT by k plus n naught e raised to RT minus 1 tends to k as t tends to infinity. We know that n naught is greater than or equal to 0 since n represents a non-negative quantity, and that is illustrated in figure 1. Figure 1 gives a qualitative study of the ordinary differential equation. Clearly, if n naught is less than k, n of t simply increases monotonically to k, while if n naught is greater than k, it decreases monotonically to k. In the former case, there is a qualitative difference depending on whether n naught is greater than k by 2 or n naught is less than k by 2. In the case where n naught is greater than k, this would imply that the per capita birth is negative, that is, the births plus immigration are less than the deaths plus immigration. The main point about the logistic form is that it is a particularly convenient form to take when seeking qualitative dynamic behavior in populations in which n equal to 0 is an unstable steady state and n of t tends to a finite positive stable steady state. The logistic form occurs very often in different contexts, primarily because of its algebraic simplicity and because it provides a preliminary qualitative idea of what can occur with more realistic forms. One point to highlight about the logistic form is its complexity. Equation 2 produces the same behavior for all solutions once the parameters b and d are fixed. Solutions simply grow exponentially to plus infinity if b is greater than d and decrease exponentially to 0 otherwise. In equation 3, the monotonicity of the solution qualitatively depends on the initial population. That is, if the population is initially higher than the carrying capacity k, then n of t decreases, otherwise it increases. This is the first step towards complexity in the sense that the model can provide for a different behavior by changing the initial data. However, it is of course very naive to name such a phenomenon as a complex behavior. A better step forward can be done by considering more general autonomous equations as follows. In general, due to specific modeling motivations, one can consider a population to be governed by dn by dt is equal to f of capital N, where typically f of n is a nonlinear function of n. Then the equilibrium solution n star are solutions of f of n equal to 0 and are linearly stable to small perturbations if f dash n star is less than 0 and unstable if f dash n star is greater than 0. This is clear from linearizing about n star by writing small n of t is equal to capital N of t minus n star when norm of n t is very much less than 1, and equation 5 now becomes dn by dt is equal to f of n t plus n star is equal to f of n star plus f dash n star into n t plus etc., which to first order in n t gives dn by dt is approximately equal to f dash n star n t, which gives n of t is directly proportional to e raised to f dash n star t. So, n grows or decays accordingly as f dash n star is greater than 0 or f dash n star is less than 0. The time scale of the response of the population to a disturbance is of the order of 1 by mod f dash n star. It is the time to change the initial disturbance by a factor e. There may be several equilibria or steady state populations n star which are solutions of f of n equal to 0. It depends on the system f of n models. Graphically, plotting f of n against n immediately gives the equilibria as the points where it crosses the n axis. The gradient f dash n star at each steady state then determines its linear stability. Such steady states may however be unstable to finite disturbances. Now, we will move on to delay models. One of the deficiencies of single population models like equation 5 is that the birth rate is considered to act instantaneously, whereas there may be a time delay to take account of the time to reach maturity, the finite gestation period, and so on. We can incorporate such delays by considering delay differential equation models of the form dnt by dt is equal to f of nt and t minus capital T, where capital T is greater than 0, the delay is a parameter. The dependency on n of t minus t in the right hand side of equation 6 accounts for the birth rate at time t being influenced by the number of individuals at time t minus t, where capital T is the gestation period. One such model which has been used is an extension of the logistic growth model given by equation 3, namely the differential delay equation dnt by dt is equal to r into nt into 1 minus n t minus t by k, where r, k and capital T are positive constants. This says that the regulatory effect depends on the population at an earlier time t minus t rather than that at t. This equation is itself a model for a delay effect, which should really be an average over past populations and which results in an integral differential equation. Thus, a more accurate model than equation 7 is, for example, the convolution type dnt by dt is equal to r into nt into 1 minus 1 by k integral minus infinity to t w t minus s ns ds, where wt is a weighting factor which says how much emphasis should be given to the size of the population at earlier times to determine the present effect on resource availability. Practically, Wt will tend to 0 for large negative and positive t and will probably have a maximum at some representative time capital T. Typically, W of t is as illustrated in figure 2. Figure 2 gives the typical weighting function W of t for an integrated delay effect on growth limitation for the delay model represented by equation 8. If W of t is sharper in the sense that the region around t is narrower or larger, then in the limit we can think of Wt as approximating the Dirac function delta t minus t, where integral minus infinity to infinity delta t minus t f of t dt is equal to f of capital T. Equation 8, which we have discussed, in this case then reduces to equation 7. Now, we have integral minus infinity to infinity delta t minus capital T minus s ns dt is equal to n of t minus t. The character of the solutions of equation 7 and the type of boundary conditions required are quite different from those of equation 3. Even with the seemingly innocuous equation 7, the solution in general have to be found numerically. Note that to compute the solution for t greater than 0, we require n of t for all minus t less than or equal to t less than or equal to 0. Therefore, the complexity of such problem is that of a functional differential equation rather than that of an ordinary differential equation, in the sense that the initial value to be assigned in order to compute a solution uniquely is a function on the interval closed interval minus t 0 and not just a real number. We can, however, get some qualitative impression of the kind of solutions of equation 7 which are possible by the following heuristic reasoning. We shall suppose that a solution n of t to equation 7 exists for all times. Since the following argument is a simple heuristics, we shall suppose for simplicity that r into capital T is greater than 1. Figure 3 gives a schematic periodic solution for the delay equation population model. We will refer to figure 3 and suppose that the initial function n naught from closed interval minus t 0 to r is increasingly monotone and such that n naught t is less than or equal to k for all t element of minus t 0. Assume further that n naught at 0 is equal to k. Take a time t1 element of half open interval 0 t. We clearly have then n of t1 minus t is less than k. Then from the governing equation 7, since 1 minus n of t1 minus t by k is greater than 0 and dn t1 by dt is greater than 0, and so the population n at time t1 is still increasing. When t is equal to capital T, n of t minus t is equal to n of 0, which is equal to k, and so dn by dt is equal to 0. Consider now a time t2 element of open interval t comma 2t, n of t2 minus t greater than k, and so dn by dt at t2 is less than 0 and n of t decreases. At time t equal to 2 into capital T, n is still decreasing since its time derivative is not 0, because dn by dt at 2 capital T is equal to r into n at 2t into 1 minus nt by k, which is less than 0 because of equation 7. We prove now that there exists a time t3 where t3 is greater than capital T such that n of t3 is equal to k. If this is not the case, then n of t would be larger than k for all times and decreasing. Suppose n of t is greater than or equal to 1 plus epsilon into k for some epsilon greater than 0 on the interval t2 element of closed interval t2t with n of 2t is equal to 1 plus epsilon k. Now set ut as log of nt by k and consider for a t2 element of 2t 3t d by dt of u of t is equal to r into 1 minus e power u into t minus t, which is less than r into 1 minus of 1 plus epsilon, which is equal to minus r epsilon, which implies u at 3t is less than u at 2t minus t into r into epsilon, which is equal to epsilon into 1 minus rt, and that is less than 0. Since we have required rt greater than 1, hence by continuity there exists a time t3 less than 3t such that u of t3 is equal to 0, which means n of t3 is equal to k. Clearly, at t equal to t3 we have dn by dt greater than 0 and n is still decreasing. The above heuristics clearly shows that there is the possibility of oscillatory behavior. As an example, let us consider the simple linear delay equation dn by dt is equal to minus pi by 2t into nt minus t, where a is a constant. We can see that nt is equal to a cos pi t by 2t is a solution and n is periodic in time. In fact, the solutions of equation 7 can exhibit stable limit cycle periodic solutions for a large range of values of the product RT, of the birth rate R and the delay capital T. If Tp is the period, then n of t plus Tp is equal to nt for all t. The point about stable limit cycle solutions is that if a perturbation is imposed, the solution returns to the original periodic solution as t tends to plus infinity, although possibly with a phase shift. The periodic behavior is also independent of any initial data. From figure 3 and the heuristic argument above, the period of the limit cycle periodic solutions might be expected to be of the order of 4t. Also, we expect this to happen for a large range of RT, which incidentally is dimensionless grouping. The reason we take this grouping is because equation 7 in dimensionless form becomes d n star by dt star is equal to n star of t star into 1 minus n star t star minus capital T star, where n star is equal to n by k and t star is equal to RT and capital T star is equal to R into capital T. This simple delay model has been used for several different practical situations. The single non-delay differential equation models for population growth without delay, that is like dn by dt is equal to f of n, cannot exhibit limit cycle behavior. We can see this immediately as follows. Suppose this equation has a periodic solution with period capital T, that is n of t plus capital T is equal to n of t. Multiply this equation by dn by dt and integrate from t to t plus capital T, we get integral t to t plus t dn by dt square dt is equal to integral t to t plus t f of n dn by dt dt is equal to integral n of t to n of t plus t f of n dn, which is equal to 0, since n of t plus t is equal to nt. But the left hand integral is positive, since dn by dt the whole square cannot be identically 0 unless n is a constant. So, we have a contradiction. So, the single scalar equation dn by dt is equal to f of n cannot have periodic solutions. Linear analysis of delay population models, the periodic solutions. We saw in the last section how delay differential equation model, the equation 7, was capable of generating limit cycle periodic solutions. One indication of their existence is if the steady state is unstable by growing oscillations, although this is certainly not conclusive. We consider here the linearization of equation 7 about the equilibrium states n equal to 0 and n equal to k. Small perturbations from n equal to 0 satisfy dn by dt is approximately equal to r into n, which shows that n equal to 0 is unstable with exponential growth. We thus need only consider perturbations about the steady state n equal to k. It is again expedient to non-dimensionalize the model equation 7 by writing n star t is equal to nt by k, t star is equal to rt, and capital T star is equal to r into capital T, where the asterisk denotes dimensionless quantities. Then equation 7 becomes, on dropping the asterisk for notational simplicity, but keeping in mind that we are now dealing with non-dimensional quantities, dnt by dt is equal to nt into 1 minus nt minus t. We linearize about the steady state n equal to 1 by writing n of t is equal to 1 plus small nt. We therefore consider the linearized equation d small nt by dt is equal to minus n of t minus t. We look for solutions for nt in the form nt is equal to c into e raised to lambda t, which gives lambda is equal to minus e raised to minus lambda capital T, where the last identity follows from the previous equation, that is the equation 12. C is a constant and the eigenvalues lambda are solutions of the second of equation 13, the transcendental equation in which t is greater than 0. It is not easy to find the analytical solutions of equation 13. However, all we really want to know from a stability point of view is whether there are any solutions with real lambda is greater than 0, which from the first of equation 13 implies instability, since in this case nt grows exponentially with time. Set lambda is equal to mu plus I omega. There is a real number mu naught such that all solutions lambda of the second of equation 13 satisfies real lambda is less than mu naught. To see this, take the modulus to get mod lambda is equal to e raised to minus mu capital T, and so if mod lambda tends to plus infinity, then e raised to minus mu t tends to plus infinity, which requires mu tends to minus infinity. Thus, there must be a number mu naught that bounds real lambda from above. We now take the real and imaginary parts of the transcendental equation in equation 13, namely mu equal to minus e raised to minus mu t cos omega t and omega equal to e raised to minus mu t sin omega t, and determine the range of t such that mu is less than 0. That is, we want to find the conditions such that the lowest upper bound mu naught on mu is negative. Let us first dispense with the simple case where lambda is real, that is omega equal to 0. From equation 14, omega equal to 0 satisfies the second equation and the first one becomes mu equal to e raised to minus mu t. This has no positive roots, mu greater than 0, since e raised to minus mu t greater than 0 for all mu t, or as can be seen on sketching each side of the equation as a function of mu and noting that they can only intersect with capital T greater than 0 if mu is less than 0. Consider now omega not equal to 0. From equation 14, if omega is a solution, then so is minus omega. So, we can consider omega greater than 0 without any loss of generality. From the first of equation 14, mu less than 0 requires omega t less than pi by 2, since e raised to minus mu t is less than 0 for all mu t. In principle, equation 14 defines mu of t and omega of t. We are interested in the value of t when mu of t first crosses from mu less than 0 and mu greater than 0. As t increases from 0, mu equal to 0 first when omega t is equal to pi by 2. In case t equal to 0, we have mu equal to minus 1 less than 0 and omega equal to 0. From equation 14, we see that if mu equal to 0, the second equation gives as the only relevant solution omega equal to 1 occurring at t equal to pi by 2. Since this is the first 0 of mu as t increases, this gives the critical value t represented by Tc, which is equal to pi by 2. Returning now to dimensional quantities, we thus have the steady state n of t equal to k is stable if 0 less than RT less than pi by 2 and unstable for RT greater than pi by 2. In the latter case, we expect the solution to exhibit stable limit cycle behavior. The critical value RT is equal to pi by 2 is the bifurcation value, that is the value of the parameter RT here, where the character of the solutions of equation 7 changes abruptly or bifurcates from a stable steady state to a time varying solution. The effect of delay in models is usually to increase the potential for instability. Here, as t is increased beyond the bifurcation value Tc is equal to pi by 2r, the steady state becomes unstable. Now, let us summarize what we have learned in this session. We have started our discussion with the continuous growth models. Under this topic, we have seen the steady state conditions for single population models like logistic growth model. Then we moved on to the delay population models and have seen how delay population model was capable of generating limit cycle periodic solutions. For further understanding of the topic, try out these exercise problems. First one, there are two steady states or equilibrium states for the equation dn by dt is equal to Rn into 1 minus n by k, namely n equal to 0 and n equal to k, that is where dn by dt is equal to 0. N equal to 0 is an unstable equilibrium state, whereas n equal to k is stable. Prove this statement. Second problem, prove that the solution of dn by dt is equal to Rn into 1 minus n by k is n of t is equal to n naught k e raised to RT by k plus n naught e raised to RT minus 1 if n of 0 is equal to n naught. Third problem, show that n of t is equal to a cos pi t by 2 capital T is a solution of the equation dn by dt is equal to minus pi by 2t n t minus t. Here are some books for further reading. First one is Life Science Models, which comes as the Modules in Applied Mathematics Volume 4, written by H.M. Roberts and M. Thompson, Springer Verlag 1982. Second one, Mathematical Modeling in Biology and Introduction by Elizabeth S. Ullman and John A. Rhodes. Third one, Mathematical Biology Lecture Notes by Jeffrey R. Kasnow. Fourth one, Mathematical Modeling Lecture Notes by Jeff S. McGough. And fifth one, Mathematical Modeling Lecture Notes by David C. Dobson. With this, we come to an end of this session. We will continue with the mathematical modeling in another session. Till then, goodbye.